Problem statement. A medical researcher, he wants to find out whether a new medication that's out in the market wouldn't have any undesirable side effects on patients' pulse rate. So the researcher is concerned with whether the pulse rate increases, or does it decrease, or does it remain the same after taking the medication. Ideally, he would want the pulse rate to remain the same. Now, the researcher knows that the mean pulse rate mu for the population under study is 82 beats per minute and that the population standard deviation is 5 beats per minute. So what the researcher does, he selects a random sample of 60 patients who take the medication and he finds that the mean pulse rate is 80.7 beats per minute. How would you test the claim that the medication does affect the mean pulse rate of the patients at a significance level alpha equal to 0.01? This session is about answering these types of questions. This session is about p-value. A p-value in hypothesis testing, it is the probability of obtaining the results as extreme as or more extreme than the observed data, assuming that your null hypothesis is true. In other words, it measures the strength of the evidence against the null hypothesis. If you have a small p-value, let's say typically they tend to be less than 0.05. This 0.05, by the way, refers to your alpha, which is your significance level. This suggests that your results are very statistically significant. In other words, your evidence is against null hypothesis. Your null hypothesis can be rejected. On the other hand, if you have a large p-value, typically more than 0.05, that would suggest that your observed results are likely due to random chance. In other words, your evidence is not against the null hypothesis. Your null hypothesis cannot be rejected. This diagram kind of like essentially captures what I just said over here. So let's understand our p-value through a simple example. Let's say your null hypothesis is the medicine does not work. That's your null hypothesis. Your p-value would be how surprising are my results if the medicine truly does not work. So let's say we choose a significance level. Let's say it's 5%. This pretty much controls our threshold for surprising result. So if my p-value comes out to be 0.001, which is actually equal to 0.1%, which is very less, that tells me that my results are very surprising because I had such a small chance of observing it. So there is a strong evidence that the medicine might actually work. In this case, you reject it. You reject your H0, your null hypothesis. And the reason you're rejecting it, because you obtained an evidence. You saw something in the sample that was very surprising. Okay, if your P is 0.6, 60%, in that case, your results are not surprising. Well, because you had a high probability of obtaining it. So in this case, there is no evidence that the medicine helps. In this case, do not reject your null hypothesis. Do not reject. Okay, do not reject your null hypothesis. This little visual diagram, it kind of helps you understand this concept over here. So your hypothesis problem, they fall under three categories. You have left tail test, right tail test, two tail test. In your left tail test, you actually find your rejection region first. All right. Then you've calculated your p-value. If your p-value is more than alpha, let's say your p-value falls, in this region right here, then do not reject your H0. If your p-value is less than alpha, in that case, you reject your H0 because your p-value will fall in this region right here. Okay, it's smaller than that. Then you have a right tail test. Same logic. Let's say this is your rejection region right here. Okay, if your p-value is greater than alpha, then do not reject your H0. If your p-value is smaller than alpha, then reject your H0. And then you have two-tailed test. In this case, your alpha will get split into two half. Right? This is because this is a two-tailed test. So you alpha over 2 will come over here. The rest of other alpha over 2 will be on this side. So if your p-value is greater than alpha, same logic, do not reject your H0. On the other hand, if your p-value is smaller than alpha, then you reject H0. So these are the steps you follow when you do hypothesis testing using p-value method. First, you state your hypothesis and identify the claim. Step 2, compute your z test value or your t test value depending on the conditions. Step 3, find the p value for the above test value. Okay, you find p value for this. Step 4, you compare the p value with the significance level alpha and you make these decisions. If your p value is smaller than alpha, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. At the end, step 5, you summarize your result. These little visual diagrams, they kind of aid you, they help you understand this logic right here. In a population of metal component, the average lifetime without protective paint coating is 101 days. Now, the lifetime is normally distributed. That's given to you. And also given to you is that the population standard deviation is 15 days. So an engineer, he claims that he has some kind of new protective paint coating that would increase the mean lifetime of the component beyond 101 days. So what she does, she tests this claim. She selects a random sample of 50 components with the coating and observes the following lifetime. So one of them lasts 114 days, the other one lasts 107 days, and 115 days, and so on and so forth. And then she observes. She calculates the mean of this, and the mean of above 50 sample comes out to be 107 days approximately. So test the engineer's claim at a significance level alpha equal to 0.05. Use the p-value method over here. We're going to follow the same steps. I just showed you these steps right here. So step 1, uh, state your hypothesis and identify the claim. Well, my null hypothesis is nothing changed. My mean is 101. The coating has no effect. My H1, which is my alternative hypothesis, that will claim that my mean lifetime, it actually increased. Okay, it actually went beyond 101 days. The coating increases the lifetime. This would be called a right tail test because of the presence of this greater than sign right here. Step 2, now I know my population standard deviation. So compute the z-test value for your mu. So in this case, substitute your, this is the formula I'm using. Okay, this is the formula to actually find your z value. So I know my sample mean, I know my population mean, I know my population standard deviation, and I know my sample size. Substitute your values in there, and the answer comes out to be 2.83. So this is my z value. Step 3, now find the corresponding p-value. So first you look up the z value in the standard normal table for z equal to 2.83. Now we know your probability of z greater than 2.83 is equal to 1 minus probability of z less than 2.83. And the reason I'm actually changing this expression to this is because this value, I can find that in the standard normal table. So finding the values over there, you come up with 0.0023. So the p-value is 0.0023. So in this case, my alpha was right here given to you 0.05. So my alpha is 0.05 and my p-value is 0.0023, which is very tiny. So it's falling somewhere in this region right here. So in this case, my p-value is smaller than alpha. So you reject your H0. Okay, so this is what I'm doing in step 4. You're rejecting your null hypothesis at 5% significance level. Now you summarize step 5. There is enough evidence at the 5% significance level to conclude that the new coating has has no effect. Now I'm doing the same problem using a computer program in Python. So it's exactly the same problem. I'm using SciPy package over here. Substitute your values in here, mu, sample mean, sigma, n, and alpha. And at the end, this logic right here, it actually checks whether my p-value is smaller than or greater than alpha. And based on that, it actually makes a decision. And the answer, as you can see, says yes, reject your null hypothesis. So a water treatment plant, it claims that their new filtration system, it reduces the contaminant level to below 5 parts per billion, which is the population mean. The environmental engineers, they want to verify this claim. So they take a random sample of 60 water samples after the treatment. Now, the sample shows that the mean contaminant level of 4.9 parts per million with a known population standard deviation of zero point 0.8 parts per million. Now test the water treatment plant claim at significance level alpha equal to 0.10. Follow the same steps. Step 1, state your hypothesis, identify your claim. My hypothesis, null hypothesis, is that no improvement, everything is same. So mu equal to 5 parts per million. The claim is that system reduces the mean contaminant level. Well, in that case, my mean is less than 5 parts per million. Since there's a less than sign, I'll be using left tail test. Step 2. Here, I know my population standard deviation, so compute your z-test value. So I'm using the same expression. This is my sample mean, population standard deviation, and the sample size. Substitute your values in there, and your answer comes out to be minus 0.97. Then you find your p-value. So look up the z-value in the standard normal table for z equal to minus 0.97. Now your probability of z less than minus 0.97 is equal to 0.1666. So the p-value is 0.1660. So in this case, my alpha is 0.10 and my p-value in this case is 0.16. So it is in this area right here. Okay, it actually comes over here. All right. So my p-value in this case, okay, right there you can see it is greater than alpha. So in this case, do not reject my null hypothesis. So in step 4, I am not rejecting null hypothesis at 10% significance level. Step 5, summarize your result. Although the sample mean is lower than your 5 parts per million, there is not enough evidence at the 10% level to conclude that the new filtration system reduces contaminant level. I'm doing the same problem using a little computer program right here. So this is a program written in Python. I'm using SciPy package. I'm substituting my values, all my mu, sample mean, sigma, n, and alpha. And then this logic right here, it based on condition, actually rejects it or does not reject it. In this case, as you can see, it did not reject it that. So a medical researcher, he's interested in finding out whether a new medication in the market, does it have any undesirable side effects on patients' pulse rate? So the researcher is concerned with whether the pulse rate, does it increase, does it decrease, or does it remain the same? Actually, he would want the medication to have no side effects. So in other words, it should stay the same. That's the ideal, his goal is. That's what he wants. So that's what he wants to check after taking the medication. Now, the researcher knows that the mean pulse rate, mu, for the population under study is 82 beats per minute. And he also knows that the population standard deviation, sigma, is 5 beats per minute. So, to investigate what the researcher does, he selects a random sample of 60 patients who take these medication and he finds that their mean pulse rate is 80.7 bpm. Now, test the claim that the medication does affect the mean pulse rate at this significance level, alpha equal to 0.01. Well, we follow the same steps. Step 1, state your hypothesis, identify the claim. Well, my null hypothesis is that nothing changes. The medication has no effect on the mean pulse rate, mu equal to 82 beats per minute. My alternative hypothesis would be the medication does affect the mean pulse rate. Your pulse rate could be higher or it could be lower. So your mu is not equal to 82 beats per minute. So this would be your two-tailed test because it is using not equal to sign over here. Now step 2, I know my population standard deviation. So compute your z-test value. So I'm using this equation right here, this expression. So I know my sample mean, I know my population mean, I know my population standard deviation, and I also know my sample size. Substituting your value, your answer comes out to be minus 2.014. So find your p-value now. So in this case, my probability of z, magnitude of z greater than 2.014 is going to be equal to 2 times probability of z greater than 2.014. That's because the symmetrical nature of your standard distribution curve. I'm assuming you know these little concepts from my previous session. Now the probability of z greater than 2.01. So let's calculate this one right here. Okay, that's what I'm doing separately. So probability of that is equal to 1 minus this right here expression. And the reason I'm using this one is because I can calculate this value through SN table, through my standard normal table. So using standard normal table, I calculate the values and the answer comes out to be 0.0222. So the p-value is 0.0444. Okay, I'm multiplying by 2 because of this right here. All right, so now I've just used this little diagram to actually assist me, to aid me, whether should I reject or not. So if my p-value is greater than alpha, now what is my alpha in this case? My alpha in this case is 0.01, and my p-value came out to be 0.0444. So in this case, your p-value is greater than alpha. In this case, you are not going to reject your null hypothesis. So that is my step 4 right here. My p-value is this right here, and my alpha is right here. Okay, so although the sample mean pulse rate after the medication, 80.7, 80.7 is lower than the population mean, there is not enough evidence at the 1% level to conclude that the medication has any effect on the mean pulse rate. That's your summary. I also did the same question using a computer program. So this is a Python program, and here I'm using SciPy stats package, and I'm substituting all my values over here, and I'm calculating my z-stat, calculating my p-value, and based on that, I'm making a decision whether I reject or not reject. In this case, I did not reject my null hypothesis.